before his talk begins, I just wanted to remind people that during his talk, please interrupt Ludwig directly with your voice if you have any clarifying questions. He'd be happy to take questions during the talk. However, any other questions, feel free to hold those until the end of the talk, in which time we will do questions with the typing hand into the chat, and we'll go one by one. So again, we're very thrilled to have Ludwig here today. He's coming to us from a postdoctoral researcher at UC Berkeley. He works with Moritz Hart and Ben Recht. He completed his PhD at MIT under Piotr Indyk, and he has received a Google PhD fellowship, a Microsoft Simons Fellowship, Best Paper Award at ICML, and the Sprouse Dissertation Award from MIT. His research interests revolve around the empirical and theoretical foundations of machine learning. It's really a mix of the two. And he often is interested in trying to look at ways that make machine learning more reliable and predictable. And so with that, today he's going to be talking about classifier generalization. And please take it away, Ludwig. Welcome.
Cool. Thanks for the introduction, Kevin. I'm excited to be here today, and I'm excited to tell you about work broadly around the question, how reliable is current machine learning? I think everyone by now is familiar with the fact that over the past decade, there's been sort of an explosion of interest in machine learning. And what is all this excitement about? What are some of the key advances behind this excitement in machine learning? And I think everyone in the field would agree the progress on the ImageNet dataset has been one of these key advances. Many of you have heard of ImageNet before. Let's just make sure we are all on the same page. What is ImageNet? ImageNet is a large image classification dataset. It contains about 1 million training images divided into 1,000 different classes. And the task that we ask the computer to do is simply, given an image like this dog here, assign the correct label from the ImageNet class hierarchy, which here would be golden retriever, and so on. You get the idea. And history around ImageNet is nicely summarized with this plot here. So on the x-axis, we have the year of the ImageNet competition. So the team around Feifei didn't just release a data set, they also held an annual competition where teams submitted their classification algorithms, and the goal was to figure out in a given year who did best. And sort of on the y-axis, you have classification error of the best submission in a given year. And initially, when this data set and the competition came out, people considered this to be a really hard problem. Like error rates were high, and it wasn't exactly clear how to make much progress. But then in 2012, a breakthrough happened. So this is when the team around Jeff Hinton from Toronto released their seminal AlexNet paper, and they showed for the first time that large convolutional neural networks could make substantial improvement on ImageNet. And then in the following years, the machine learning and computer vision communities really went with this approach and had a lot of success improving the error rates on ImageNet further and further. And by some measure now, take this with a grain of salt, we'll return to this later, but by some measure now, we are at superhuman performance levels on ImageNet. And this has been tremendously impactful. So in academia, for instance, Jitendra Malik calls the AlexNet paper the most impactful paper in machine learning and computer vision in the last 5 years. This is, I think, quite uncontroversial. The ImageNet paper itself won the CVPR Test of Time Award last year. AlexNet was mentioned in the Turing Award citation last year. And the ResNet paper, which won the competition in 2015, was the most cited paper in all of the sciences last year. Okay. This is the impact in academia. Then in industry, a lot of the research labs actually joined this competition fairly early on. In 2014, a team from Google won. In 2015, a team from Microsoft won. The researchers are now at Facebook AI. And overall, companies have invested large amounts of money into machine learning research as a result of all of this excitement around machine learning. And then finally, last year, ImageNet also arrived in government. This is from the Economic Report of the President 2019. It has an entire chapter devoted to the impact AI will have in the US economy. And then the first figure in this chapter on AI is again exactly the same ImageNet plot, which is used here to convey to people how much progress we have seen in machine learning. And to be clear, it's not just ImageNet. This is sort of representative for a whole variety of different benchmarks in computer vision, natural language processing, and other fields of machine learning. We have seen sort of tremendous progress over the past decade in a variety of benchmarks. And overall, this is great. And so the ambition for our field now is to use these emerging technologies in a variety of different applications. for instance, transportation, as in self-driving cars, healthcare, robotics, online content moderation, and so on. And I think this is great. If you can use machine learning well in these different areas, I think there's the potential for real societal benefit. I think we also need to be careful. And I think one key question here is always, how reliable is current machine learning? Okay. And how do we even think about this to begin with? So what can we learn from these machine learning benchmarks? Sort of an optimistic interpretation of this plot here would be that we have truly surpassed human level performance on ImageNet, and we can now do ImageNet image classification better than humans. If you work in this area, it's pretty clear that things are more nuanced, and this is pretty optimistic. So why do we get so excited about these performance numbers? In the end, what does good performance on a test set imply? And for that, we have this concept of generalization in machine learning. This is arguably the main goal in machine learning. We want to get models that generalize. And what we mean by that is, at the very least, the classifiers should perform similarly well on new data from the same source. A bit more concretely, in the context of ImageNet, what do we mean by that? So there's some data source. Concretely, if Feifei's team used Flickr, the photo hosting website, as a source for their data set, then they got a large set of candidate images from Flickr. This is still quite noisy, so we need to do some amount of data cleaning. They used mechanical Turk for that, so crowdsourcing. And then you have a nice clean data set. You can feed it into your favorite ConvNet. So when we looked at this last spring, so February 2019, the state-of-the-art top one accuracy on ImageNet was 83%, okay? And how this idea of generalization is, there's nothing special about these specific images. Theoretically, if we generated a new data set from the same source, following the same data cleaning process and feeding it into the same ConvNet, we should get roughly the same number back. Not exactly the same number. In the end, this is a random process, but the test sets are quite large, so the error bars are quite small, and you would expect about 82 to 84% accuracy, okay? And at Berkeley, we wanted to understand, so how reliable is this generalization story? So what would happen if you actually instantiated this experiment? And this is what we did in the paper with the same name, do ImageNet classifiers generalized to ImageNet. So this was a big experiment, took us almost a year. Here it's sort of summarized in half a slide. And the point is, at the end, we had a new test set. We'll go into the details of how we build it later. But when we fed this into the state-of-the-art classifier, we didn't get 83% back, but we only got 72%, okay? To put this in context, this is an 11 percentage point drop. On an ImageNet, that's a lot. This corresponds to about 5 years of progress in a very active area of machine learning research. So this is clearly an issue. And sort of the main message of the talk is that there's going to be good and bad here. There is overfitting, but not in the form we think about it. And it's clear that we need to understand this better, okay? So at a high level, this is what the talk is about. In the first part, we'll do a deep dive into this experiment that I just summarized and try to understand exactly what causes machine learning to be unreliable. And the outcome is going to be, it's not overfitting through test set reuse, but even small variations in how you build the test sets can lead to large changes in the model accuracies. And in the second part, we will look at one facet where we have learned over the past 2 years how we can make machine learning more robust. So for experts, this is going to be about adversarial robustness. So this is what the talk is mostly about, and these are important points. The way I think about this, and something to keep at the back of your head throughout the talk, is sort of this maybe a bit more fundamental question. How do we gain reliable knowledge about machine learning in the first place? As I said, we'll only return to this at the very end, but keep this at the back of your mind. Okay, cool. So what causes machine learning to be unreliable? What's going on in this experiment? And arguably, you have a simple answer for this in machine learning. Clearly, the models are overfit, okay? But what do we actually mean by this? So in machine learning, there unfortunately is 3 different mechanisms that we use the term overfitting for. And to understand it in more detail, what's going on, we need to be more precise. So the first notion of overfitting that's commonly studied in machine learning is this comparison of test error and training error. This is a key idea in generalization theory, and this is very important, but it's not going to tell us what's different between our 2 new test sets, okay? So we'll ignore this for the rest of the talk. Instead, one overfitting mechanism that we'll look at in more detail is this idea of overfitting through test set reuse. We've used the ImageNet test set many, many times and used feedback from the ImageNet test set to develop our models. Maybe they're only good on the specific images in the ImageNet test set now. And then the third mechanism, the third overfitting mechanism that we look at is what we call distribution shift. This is the idea that small changes in the data set do creep in, and maybe the small systematic differences are substantial enough to lead to large accuracy drops. Okay, so think of these at a high level as two hypotheses that we'll tease apart with our experiment. And to be a bit more precise and to convince ourselves that these are the right notions to look at, let's be a bit more formal about this. In particular, what we want to understand is this accuracy difference here. So the accuracy on the original test set S of a given classifier F versus accuracy on the new test set S prime. And I put a hat on these accuracies because these are finite sample estimates. Nothing special going on here, just the average 0-1 loss over the examples in our test set, okay? And overall, as we said, these are 11%. This is what we need to account for. And we'll do this in 3 parts. The first part is what we call overfitting through test set reuse. And this is the gap between the accuracy on the finite test set S and the accuracy on the corresponding data distribution D that the test set S is drawn from. So I put this here at the bottom left, no hat anymore, because this is now the true average at the distribution level. So this is an expectation of the 0-1 loss. And the problem here is that the classifier F may depend on the test set S, and this is why we don't have an easy way of bounding this. The second term is now entirely at the distribution level. This is simply the accuracy difference between existing test set distribution D and new test set distribution D prime. And then in order to make the equality work out, we need a third term. And the good news is this third term is easier to abound. So this is now the difference between the new test set distribution D prime and the new test set S prime. And now here, since the test set was built after the model F was fixed, we can just use standard concentration results to get a handle on this third term. And we can say with high probability, this third term is at most 1%. So the remaining at least 10% need to be in either the overfitting through test set reuse or the distribution shift term. Okay. So what we do now is do a deep dive into these 2 terms to understand to what extent they're responsible for the accuracy drop. Okay, so first let's look at overfitting through test set reuse. Why is this an issue? Okay, let's begin with what is the ideal machine learning workflow? How do we teach machine learning in an ML 101 class? Typically what we teach is if you want to do machine learning, you build a data set by first collecting a large amount of data, and then you split it randomly into a training set, a validation set, and a test set. And from the beginning, we sort of set the test set aside and never touch it until the very end. That's the contract. So we build our model by training on a training set, then tuning hyperparameters on the validation set, and we repeat that many times until sort of the end, the day before the ICML deadline, we have our final model. And then only at the very end, when the model is fixed, we use our test set, feed it into the classifier once, and then we get our final accuracy number out, say 84%. And because we've never used the test set so far, this is indeed a valid estimate of the population accuracy. So we can put this into our paper and we can be confident that there's no problem with overfitting. Okay, so that's the ideal scenario. Unfortunately, this is not how machine learning typically works these days. Machine learning has become a very competitive field. And also some of the data sets don't even come with a validation set anymore. Like for CIFAR-10, for instance, we'll return to that in a second, there's only a training set and a test set. And how this typically works now is people want to improve over the state of the art because that's the way to get a paper accepted. So we download a model that's already doing quite well. The problem is this is already some adaptivity that creeps in. So someone has tuned that model on the test set and we start out with that. And then we do further development, we train on a training set, but often what people do is they select the best model, the best hyperparameters based on feedback from the test set. Okay, so there's more adaptivity coming in. And now the next deadline comes around, say NeurIPS, we have a larger model, we get higher accuracy, but what does this really mean? So we don't have any nice formal guarantee anymore that these 90% are indeed a valid estimate of the population accuracy. Okay, there's a question mark here. And we are certainly not the only ones to point this out. Like this is a classical theme in machine learning. For instance, Kevin Murphy's widely read textbook calls it a golden rule of machine learning not to use the test set for model selection, because otherwise we will get an overly optimistic performance of our estimate of our performance. This also appears in dataset papers like Pascal VOC was the main image classification challenge before ImageNet. And in the dataset paper, they clearly say they needed to build a new test set every year in order to avoid participants overfitting to the test set. Last year, a group built a new test set for MNIST, And then Jan LeCun, Turing Award winner last year, sort of called on the community to evaluate the MNIST models also on the new test set, because the assumption is that probably people have overfit to the existing MNIST test set because it has been around for so long. And this also often appears sort of in online discussions or blog posts. Here's one that specifically calls out progress on the ImageNet dataset is probably overfit. And to be fair here, there's cause for concern, because in the ImageNet competition, they did not build a new test set in every year. Instead, the test set that was used in 2012 is the same test set that they used in all following years. So maybe people have really overfit to this test set. And then the worry is that overall progress in the community looks more like this. If you think sort of as a sketch, this is not real data, just a sketch. X-axis test set accuracy, Y-axis the true accuracy on fresh data, if we had fresh data and sort of deployed the model. And then the issue is that if we overfit to the test set, over time, we only make progress on the x-axis, only on the test set, but we don't really make true progress on new data anymore. And then this gap between the dashed line, which is sort of ideal generalization, and what's actually happening, the blue line, would be this overfitting from test set reuse. Okay, how do we figure out to what extent that's happening? And what we did in our ImageNet experiment is the following. So this is one of the key plots in the talk. So I go through this step by step. X-axis original accuracy on the original ImageNet test set. Y-axis accuracy on our new test set. And to orient ourselves, this is again the no change line, y equals x. And now we build a large test set of ImageNet classifiers ranging from AlexNet to the state of the art in early 2019. As I already mentioned, the best model from early 2019 sees an 11 percentage point drop. Okay, this is bad. So now the question is, where do the other classifiers fall? And then you get the following. This is very surprising. So it's not just that the best model from early 2019 drops. In fact, all of the models drop by roughly the same amount. So the relative ordering of the models is very nicely preserved. In fact, it's an almost perfect linear fit. And also the AlexNet model from 2012 drops. If anything, it drops by a little bit more. So the absolute numbers change, but the relative ordering is well preserved. And we did a similar kind of experiment also on another data set, CIFAR-10. This is again image classification. And overall, the picture here is quite similar. So again, all the models are below the dashed line. So all the models see lower accuracy on our new test set, again, built in a very similar way. But one thing that's striking here is that the slope of the line is substantially steeper than 1. So what does this mean concretely? So if you look at the state-of-the-art model, auto-augment, and compare its performance to a ResNet. This is in this blob here. It's about a 5 percentage point different on CIFAR-10, but this grows to a 10 percentage point different on CIFAR-10.1, okay? And this is important. This is exactly the opposite of what you would expect under this overfitting through test set reuse scenario that we had earlier, right? We said over time, if there's overfitting through test set reuse, these accuracies would plateau. And if anything, what we see happening on CIFAR-10 is that the later models are better. They are not more overfit, but they actually see a smaller performance drop than the earlier models, okay? So this was very surprising to us. This is the exact opposite of what you would think would happen if you reuse a test set many years. And we have, or the community has reused CIFAR-10 and ImageNet for 10 years in a very competitive process, and they have effectively no sign of overfitting through test set reuse. This is really good news for the benchmarks. The relative ordering is preserved, and the progress we have seen on these benchmarks is real. There's really no doubt about this anymore. But on the other hand, as I said, this is also quite surprising. So we were curious what happens on other data sets. Another one that I already mentioned is MNIST. So after our paper came out, Duff and Boutou did a similar experiment as a follow-up. And this actually has a quite nice backstory. So what happened there was that Leon saw our paper, Leon Boutou, and he thought like, okay, what's going on MNIST? This is really interesting. And the funny part here is that when they built MNIST, they actually built a larger test set of size 60,000 examples, but they only released 10,000 examples. At the time they thought, we'll release the remaining 50,000 examples soon. But effectively, they procrastinated on this for 20 years. And then after Leon saw our paper, he thought like, okay, now it's time to get out these remaining 50,000 examples, because he wanted to know for sure if they had been overfitting on MNIST or not. And then their paper reaches very similar conclusions. They nicely say that in their abstract, that they observe the same trends as in our paper. And so again, the misclassification rates are slightly off, and the classifier ordering and model selection remain reliable. So again, good news for the MNIST dataset. But again, this is only a small part of machine learning. It's still image classification. So at Berkeley, we wanted to know what's happening in machine learning more broadly. And for that, we went to Kaggle. So Kaggle is a large platform for machine learning competitions. And we looked at the 120 most popular classification competitions on Kaggle and did a meta-analysis of these competitions. And at a high level, the takeaway is that there's also little to no evidence of overfitting through tested reuse on Kaggle. So if you plot public versus private accuracy on the Kaggle test sets, you always get these nice diagonal plots. So the scores match. There's none of this plateauing behavior that people were worried about. Okay, so this is surprising. What's going on here? What is protecting us in the machine learning community from overfitting through test set reuse? And I think this is a question we still need to understand better. There are multiple different mechanisms that people have proposed why there's little adaptive overfitting. One specific one that we looked at in Berkeley over the past year is this idea of model similarity. So at a high level, what we do in this paper is we propose a way of measuring how similar two ImageNet models are. Because what we observed is that overall, the ImageNet models are substantially more similar than what you would expect if the model errors were uncorrelated. And this is an important insight because once you have this notion of similarity and you can show that the models are quite similar, you can build a theory around this and show in a provable way that this amount of model similarity on ImageNet already protects you to some extent from overfitting through test set reuse. So on the plot on the right, we can see that for the model similarity that we are in, the regime that we are in on ImageNet, depending on the assumptions you make on the theoretical side, you get a roughly 10 to 1,000x increase in the number of models you can test before you start overfitting. Okay, so this is just a sort of high-level picture here. As I said, there's more going on. If you want to learn more about the lack of overfitting here through test set reuse, then I recommend you have a look at Moritz Hart's keynote at Cold last year. For now, we are going to close the overfitting through test set reuse chapter. We're going to return to the high-level question: where does the accuracy drop come from? So as I said, this is the decomposition into 3 parts. And now we can say there's overwhelming empirical evidence that it's not overfitting through test set reuse. So this is 0%. And that means at least 10% actually do need to come from this distribution shift term. So let's understand it in more detail. Okay. And in order to understand what's changing at the level of the ImageNet data distribution, we first need to talk a little bit about how was ImageNet built to begin with. Okay. So let's do that. This process, ImageNet dataset creation process, is nicely described in the dataset paper. And at a high level, it's the following steps. So first, you need a set of classes. They have 1,000 classes, and they took these classes from WordNet, which is a large database, hierarchical database of words in the English language. And then you get your classes, and with every class comes a set of synonyms. For instance, goldfish and the Latin name for goldfish. And then what they did was they used these synonyms as search terms in the Flickr API. And then Flickr gave them a set of images. And as I said, this is still a noisy data set. So you need to do data cleaning. And they used mechanical Turk in order to have the Turk worker select which images should be in the data set. Then you get a nice clean data set. You sample a class balance subset, and that gives you ImageNet. Okay. So now where do the differences come in that we have in our reproduction at Berkeley? So at a high level, we did exactly the same steps. We obviously used the same classes. We used the same Flickr API with the same search queries. We used a very similar mechanical Turk process. And obviously at the end, we also sample a class balance data set. So where do the differences lie? One question we often get is, what about time? We did this experiment in 2018, 2019. This is 10 years after the original ImageNet dataset was built. And clearly in these 10 years, some objects have changed a lot. So for instance, a cell phone now looks quite different from a cell phone 10 years ago. But we were very much aware of that when we built our new test set. And a nice aspect of the Flickr API is that you can select a time constraint on your search query. So we told the Flickr API, only give us images from a similar time range as the original ImageNet dataset. So this controls for temporal distribution shift on the Flickr side. Our hypothesis that even small variations in how you do the mechanical Turk process can have large impact on the classifier accuracy. So for us, the mTurk part is the likely source of distribution shift. And to convince you of that more, we look at this in more detail now. And so first of all, how do you even use mechanical Turk to build ImageNet? And the main task that you ask the workers to do is the following. You show them a grid of images with a certain candidate class already predefined. For instance, these would be candidate images for the class bow. And then the instruction is, please select all images containing a bow. So the worker would do that. These are the images containing a bow. And you don't just do this once, because otherwise it would be too noisy. So you replicate this in the case of ImageNet, and in our experiments, we replicated every grid of images at least 10 times. And what you in the end get for every image is what we call a selection frequency. This is the number of workers who selected an image divided by the number of workers who saw an image. And you can think of this as a rough measure of quality. Images which very clearly show a bow get high selection frequency. Images that have nothing to do with a bow get low selection frequency. Images where the bow is smaller, like here, are somewhere in the middle. Okay. And then the question is like, what do you do with these selection frequencies? How do you build a data set out of this? And this is a tricky part now, because the exact details are unfortunately lost. But what we did was sort of a best effort, in the sense that we piped the existing ImageNet test set through our annotation process as part of building our new test set. And from that, we got an average selection frequency for the existing test set. And then we built our first test set, which we here call approximately calibrated, so that the average mechanical Turk selection frequency roughly matches what the existing ImageNet test set has. There are some details, but overall, this is the high-level picture. And then you see roughly a 12 percentage point drop in accuracy across our model test bed. But now the obvious question is like, can we use our candidate set of images also to build easier data sets that don't have the accuracy drop? And so we explored this with two different data sets for the purpose of this talk. Let's just call them easier and easiest. These dataset sampling strategies lead to higher mechanical Turk selection frequencies, and correspondingly, this is crucial, they also lead to higher accuracies for the ImageNet models. So in fact, on our easiest dataset that we could build with our candidate pool, the models actually see higher accuracies than on the original ImageNet test set, okay? So first of all, this clearly shows that the MTurk process through the selection frequencies can have a large impact on the classification accuracies. And another crucial part that's important here is all the data sets are correctly labeled. This is not an effect coming from the fact that some images are just mislabeled. Becca, Weichel, and I carefully went through our test sets many times to make sure the label quality is high. And now you can ask the question, okay, which data set here is the right one? Should we calibrate based on mechanical Turk selection frequencies? Should we calibrate based on the ImageNet scores? And that's a good question, but I would say, sort of at a high level, the models shouldn't really be so susceptible to these small differences to begin with. Like when you look at these images as a human, you don't really see a big difference across this data set on average. And the expectation from a human perspective is that you should get the same accuracy on all of these three data sets. But of course, this is just an intuition. And we were curious, can we make this more rigorous? Like to be precise, what about humans in this plot here? Where would humans land compared to the models? If you believe that humans are more robust classifiers, they should land somewhere on the dashed line here and get the same accuracy on the original and new test sets. Okay, how can we find this out? So to give up a little bit more context here, let's return to this plot here from the beginning, ImageNet progress over time. I mentioned that we have this human baseline for ImageNet. One thing to keep in mind here is that this is actually only a single human. This is the accuracy that Andrei Karpathy achieved when he did this experiment on himself for a blog post that he wrote in 2014. And he did this in order to get context for the performance numbers from the 2014 ImageNet competition. It's awesome that Andrei did this. Without this number, we wouldn't have any context. But I think it's also an interesting question, like how much variation would we get around this number from Andrei's experiment? And do humans see a difference between existing test set and new test set? Okay, so this is what we wanted to understand at Berkeley. Do humans see a drop in accuracy on our new test set? And again, this was a pretty long experiment, took us actually more than a year. And I'll only give you the high-level summary here. First, we sort of carefully re-annotated the original and new test sets to make sure we have very high annotation quality for both original and new test set to make this a meaningful task. And then we trained and evaluated 5 expert labelers on 1,000 images each from the original and new test set. So we took these 1,000 images each, randomly shuffled them. So we didn't know what we were labeling when we labeled, and then just each of us labeled these 2,000 images independently. And then what you get is the following. So this is again, original versus new accuracy. And now you see that the orange points here, the 5 humans, do fall very close to the dashed line. They are all within 1% of the dashed line. One of them is actually above the dashed line, so that human is doing better on the new test set. And you can see a clear qualitative difference between human performance here and model performance. And I think this is very interesting because basically what we've done here, we've added a second performance dimension to the ImageNet task that humans effectively solve implicitly. Like when you do this as a human, at least subjectively, it's not harder to classify the new images, but the models have a really hard time generalizing to the new test set. Like there's the systematic drop. And one interesting data point here is also this green one. So I highlighted this one because this is a model trained on a lot more data. This was an experiment done by Facebook. They trained an ImageNet model on 1 billion images from Instagram. So 1,000 times more data than the ImageNet training set. And even training on 1,000 times more data is far from closing the gap. It's a little bit above the red line given by the other models, but this problem here is not easily solved just by training on more data. Okay, so far so good for image classification. I'm always interested, as in the case of overfitting through test set reuse, to what extent are these universal phenomena that happen in machine learning more broadly? So we did, again, this is just a one-slide summary of a longer project. We did a very similar set of experiments for natural language processing, in particular the Stanford question answering dataset, and effectively built a set of new test sets for a squad. And then the high-level takeaways are exactly the same. There's no overfitting through test set reuse, but the classifiers are quite susceptible to small changes in how you build the dataset, but human performance is more reliable. Okay. So these are the experiments that we did. What are the takeaways for machine learning? So I think one clear takeaway is that distribution shifts are a real problem, even if you work in a carefully controlled reproducibility experiment. And I think this is really the fundamental challenge that we have in machine learning at the moment, that often these models fail in ways we don't really understand yet. And this has direct sort of implications, again, for the application areas we mentioned earlier. So for instance, self-driving cars is a good example, and specifically the promises made by Elon Musk and Tesla. So the initial promise was by end of 2017, Tesla would have an autonomous coast-to-coast drive. Then in early 2018, Tesla was like, not quite there yet, maybe 3 to 6 months. Then some time passed. And in July last year, Elon tweeted, parking lots are a remarkably hard problem, doing an in-depth engineering review of enhanced summon later today. So enhanced summon is the feature they built where you can have your car drive towards you from the other end of the parking lot. So instead of coast to coast, we're now doing 20 meters in a parking lot, and it's still remarkably hard. And then, to be fair, they released this feature, and I'm sure it works in many cases, but you also quickly had videos like this appear on the internet, where the person is calling the car to drive towards them, and the Tesla would have hit incoming traffic if they hadn't stopped it. And this is the benign end of the spectrum. People have died in accidents due to Tesla's autopilot, and one person has died in a crash with the Uber self-driving car. I think it's very much a challenge at the moment for machine learning. So how can we make these models more reliable, and how can we test them to actually certify that they are as reliable as we would like them to be? And this is not just transportation. This also comes up in healthcare. This is another area I mentioned. So this is a nice paper which does a generalization experiment for X-ray chest classification. And then the conclusion in the paper is, so I'm quoting the paper now. So they say, even in the absence of recognized confounders, we will caution, following Recht and colleagues, so they're referencing our paper here, that current accuracy numbers are brittle and susceptible to even minute natural variations in the data distribution. So these phenomena that you see in the benchmarks are very much representative for challenges in concrete applications of machine learning as well. I think this has implications for how we should evaluate machine learning. So the current paradigm often is that we build a data set, as I mentioned, by splitting it randomly into training, validation, and test. And that's a good starting point, but it's important to remember we're not learning that much from having separate validation and test sets. In the end, in effectively all the classification competitions we looked at, validation and test set accuracies are agreeing, but that's not a good measure of reliable generalization. This is just telling us that there's no overfitting through test set reuse, but that doesn't seem to be happening anyway. So I think what we need to be doing instead is build new test sets by introducing small variations of the existing data set creation process. I think what these small variations are is a very good research question, but overall going a little bit away from the training distribution can give us a better sense of how reliable these models currently are. Okay. Cool. So this was the first part of the talk. The conclusion is no overfitting through test set reuse. but small distribution shifts are already a challenging problem for machine learning. Now, in the second part of the talk, let's look at one facet. We have made some progress in making machine learning more robust. And just for context here, we are definitely not the only ones who are saying that robustness is a challenge for machine learning right now. The distribution shift is one facet here, but there are many others. So one that we'll talk about more now is adversarial examples. There's been lots of effort in this direction. And there are many other sort of failure modes of trained models that people are pointing out in the moment. So various image corruptions that people are looking at. You can fool models with small rotations and translations. And overall, this is a quickly growing area. So Nicolas Calini, one of the researchers in this area, is keeping track of all the papers on adversarial robustness. And yeah, there are, I guess by now, sort of roughly 1,000 papers being published on this topic alone per year. And this also has a long history, obviously. So when you want to trace this back, there's a paper from Abraham Bald in 1944 with the title Statistical Decision Functions which minimize the maximum risk. So sort of 70 years, 80 years later, this is still very much the same topic that we are interested in. Okay, so for now, let's look at adversarial examples. I'm sure many of you have seen this before. The idea is that you can take an image that a classifier gets correctly, like this pig, add a little bit of carefully tuned noise. It needs to be carefully tuned, but it's easy to find. And then you can fool the model to basically say whatever you want. For instance, it will misclassify this pig here as an airliner. And in a security setting, this is very much a challenge. So what can you do about this? And this is work I did with my collaborators back at MIT, where I did my PhD. And just to give you some context, before we started to look at adversarial robustness, the state of the art was roughly an arms race between attackers and defenders, in the following sense that one group would propose a new attack, a new way to construct these small perturbations. Then another group was proposing a defense that worked against that specific attack. But unfortunately, what happened almost always is that soon thereafter, another group was propose a different attack or fine-tune the existing attacks in order to break the new defense. And this happened over and over again, so that eventually Nicolas Calini, one of the main people on the attack side, started writing papers like this, bypassing 10 detection methods, because there were so many papers coming out that he could easily break. He sort of started batching the attack papers he wrote into these larger meta papers. So this is very much not robust. And so what can we do about this? And what we are thinking about at MIT is that when you want to be adversarially robust, you really need to think about a fundamentally different optimization problem. So this is how we typically optimize our models in machine learning. We want to minimize over model parameters the expected loss over data distribution, okay? But now when you have an adversary in the picture, what you actually want is the following. You minimize over the model parameters. You still take an expectation over data distribution, but now you maximize over some perturbation set before you feed the example, the perturbed example, into the loss function. Okay, this is what we would like to get. And the idea is, if we can truly get such a min-max guarantee, then we would be robust against any attack. Then we can sort of put an end to the arms race. But the obvious question is like, how do you actually get a min-max guarantee like this? And that's where our background in optimization theory came in handy. So in particular, there's a classical result in optimization, Dunskin's theorem, which tells you how to take the gradient of a function that's defined as a maximizer of another function. And the idea is simply that you take the maximizer and then the gradient of the inner function at that maximizer. Like it's overall, this maximization over another function is exactly what we have in this robust loss function. Now the tricky part is, okay, how do you actually find the maximizer? And this is unfortunately a hard problem in the sense that people before us had already shown that it's NP hard to find that maximizer exactly already in a simple network. So you can't hope to get a nice sort of end-to-end guarantee anymore. What we found empirically though is that a few iterations of projected gradient descent already performed very well empirically in at least approximating that maximizer. The question is, what do you do with this? So we plug this into a training procedure, basically robust optimization. And at the time, we got the state-of-the-art accuracies on MNIST and CIFAR-10, the main two benchmarks in this area. But now, as I said, this is empirical. So the question is, are these models really robust? So the first thing we did was we sort of put out two nicely polished GitHub repositories to make it very easy for the community to attack our models. And this has been out now for almost 3 years. And there has been no progress beyond maybe shaving off 2 or 3%. And it's not because people didn't try. So Nicolas Collini and collaborators continued to break models. This is a table here from their ICML paper in 2018. They actually won the ICML Best Paper Award for that paper. And because what they showed is, again, they could break all proposed defenses except ours. So the highlighted line here, 47%. This is exactly what we put in our paper. They were not able to break this. Okay, and at a high level, this is still a summary of the state of the art. The highest robust accuracy numbers that we have at the moment follow the robust min-max optimization approach that we introduced in our paper. To be fair here, there's sort of also a separate line of work on methods which come with provable guarantees for robustness. So Siko Kolter's group has done work on that, and also some work from Stanford, like John Ducci and Percy Young's group. But in terms of, you just look at the accuracies that we can't currently break, this min-max approach is still giving you the best numbers. Of course, this is still empirical. So you could worry, and this is a good thing to think about, what if next week people find a better attack, and can they maybe that way break our model? But by now, we actually have good evidence that this is not going to happen. So in particular, Nicolas and collaborator, and also in a paper from Alexander's group, they did the following type of experiment. They used this robust optimization approach on a small enough problem so that you can, at the end, just take the trained network and use an exhaustive verification method on the trained network. So for endless scale problems, that works. So you don't get a guarantee from how you train the model. You just take the model as a fixed black box and then verify that it has certain properties. And they show in these papers that the model that comes out of min-max robust optimization is indeed provably robust. So we know for these models, there's not going to be an attack which is going to break this model. So that's good. And there has been lots of follow-up work that we could talk about now. People have scaled it up to ImageNet. People have used it for different perturbation sets and so on. For the remainder of the section, I'd like to focus on why did we get stuck at 47%. On MNIST, this works substantially better. And when you look at the details of training these models and to be adversarially robust on CIFAR-10, the interesting phenomenon is that on the training set, that actually works really well. On the training set, you effectively get 100% robust accuracy, but it fails to generalize to the test set. There you got only about 50% accuracy. There's a large gap between training and test set. And then we were wondering, is there maybe some fundamental reason for why you would see this behavior? And this is a paper we wrote in Alexander's group together with Kunal Talwar, who back then was a Google brain, is now at Apple. And the question we asked, does robust generalization maybe require fundamentally more data? And we show in a simple data model that this is the case. Already in the simple data model where you classify data coming from two Gaussians, you can show that there's a square root D sample complexity separation between standard generalization and adversarial robust generalization. Okay, so by analogy, this is sort of a nice piece of evidence that adversarial robust generalization may just be a fundamentally harder problem. What I often try to do is ideally connect these theoretical insights back to the empirical side. Like, can we use these theoretical ideas in order to also improve the empirical state of the art? And the nice thing is that this happened here. So in the meantime, so now I'm going to talk about work with collaborators at Stanford. So what happened in the meantime was that a group from Berkeley and CMU improved over the result Alexander's group and I had, and they got to 53% on CIFAR-10. And then I was curious, okay, if this more data limit is really the bottleneck, can we train a better model, higher adversarial robustness, by using more training data? And the answer is yes. And a nice aspect here is that we don't even need more labeled data. Unlabeled data suffices already. Initially, I was a bit worried that you would have to do a lot of labeling to make this work, but then we found out that unlabeled data is already enough. This was actually motivated by insights also from the theoretical model. And this is joint work with Yair, Aditi, Percy, and John. And at a high level, what we do there is we use a just high accuracy standard model to generate pseudo labels for our unlabeled data. And then we do robust optimization on the data, on the larger unlabeled data, using the pseudo labels just as true labels. We call this robust self-training. It has theoretical guarantees. And as I said, on the empirical side, we do get state-of-the-art robust accuracy. So if you combine the labeled CIFAR-10 data with unlabeled data from tiny images, you get 60% adversarial robustness. And this is, as of now, still state-of-the-art. So the nice thing is you could connect back and sort of close the loop between the theoretical and the empirical side. Okay, so this is all I want to say about adversarial robustness. How do the two parts fit together? So at a high level, how I think about this is that there's a lot of work at the moment around robust machine learning. This is something we clearly need to understand better. And you can sort of organize this as a spectrum. At the one end is the very worst case world, like adversarial examples, where someone really tries to fool your model. And at the other end of the spectrum, this is the first half of the talk, are these distribution shifts. Here we try to be as benign as possible in order to really recreate the existing distribution. So this is the entire spectrum, so from more average case to worst case. And a good question are like, what is in the middle? And collaborators and I, both at MIT and at CMU in Berkeley, we have some works on this. In the interest of time, I'm not going to say more here, but feel free to ask me about this later. And another question is like, how well do current robustness methods, how much do current robustness methods help on this new ImageNet dataset? As we said, ideally a robust method, just like humans, would land on the dashed line, get the same accuracy on the original and new test set. So we thought, okay, maybe something already helps here. So we built a large test set. This is ongoing work at Berkeley. The baseline here are just the models trained on ImageNet. We would like to improve over this baseline here, the red line. And then the sobering outcome was that we took everything out there, not just L-infinity adversarial robustness, also other methods that people had proposed. And these are the brown points. And the takeaway is that the brown points effectively follow the same trend as the standard models. So current robustness interventions do not help close the gap for the new ImageNet test set. One thing that helps a little bit are these green points here. These are models trained on a lot more data. So I already mentioned this experiment here, trained on 1,000 times more data at Facebook. This data point here at the very right is trained in a similarly large experiment at Google. They trained on 300 million images, so 300 times more data than the ImageNet training set. So the takeaway is that yes, more data helps, but only by a small amount. So we are not going to solve this just by throwing more data at the problem. Okay, and I think this is already pointing towards a very clear direction for future work. Sort of the current tools plus just more data and compute, they are not going to close these accuracy drops. So what can we do on the algorithmic side in order to make the models more robust? So we know we have some tools now that work in some settings. Maybe we can take some of the ideas that work for adversarial robustness and also make them work in the more benign distribution shifts here. I think this is one facet. The other one is, what are good benchmarks for promoting robustness? In the sense that what are the types of robustness that we want our models to have when we deploy them in the real world? And then how can we make sure that these are the notions of robustness we measure with our benchmarks? The second direction is, what about machine learning in more interactive settings? Everything I told you so far in this talk was this classical supervised learning setting, and it's a good starting point. But I'm also curious what happens in more interactive forms of machine learning, like causal inference or reinforcement learning. And I think here, simulation is going to be an important tool in order to probe the performance of the models that we train from data. And we've already done some work in this direction with Moritz's group back at Berkeley, building a test bed for causal inference by using domain knowledge that people have encapsulated in various simulators like epidemiology, climate economy models, and so on, and seeing if causal inference methods can figure out these simulators. And in a third direction that I'm very interested in is studying data sets in addition to models. So over the past decade, we've become very good at this framework of here's a fixed benchmark data set, and then iterate by making better and better models over time. And this is good. These improvements accumulate over time, but we don't have a good understanding what made ImageNet such a good data set to begin with. The fact that it supports progress for a decade is highly non-trivial, and the fact that it supports transfer learning quite well is also not something you would necessarily expect. So I think understanding sort of what makes ImageNet a good data set and having some guidelines for producing sort of new data sets in machine learning, both for academic use and for people in industry, I think is an important question. Cool. So for the last 2 to 3 minutes, let's return to the iceberg, right? At the beginning I mentioned there's this overarching underlying question, how do we gain reliable knowledge about machine learning? Because one topic that has sort of come up a couple of times in the talk is that some of the sort of conventional wisdom that we have in machine learning doesn't hold up that well under closer scrutiny. So for instance, lots of people told us that tested reuse would lead to overfitting, but then we looked at a lot of different highly competitive machine learning benchmarks, and there's effectively no evidence of overfitting through test set reuse. Similarly, many people have said that neural networks have now surpassed human-level performance on benchmarks like ImageNet. Once you take a closer look, things are actually a lot more nuanced. And then another point that has come up in the talk is to what extent the robust model is actually more robust. So Nicolas Collini has done lots of important work here to test proposed defenses. And there's also this question, how does one notion of robustness transfer to other notions of robustness? Okay, I mean, to be fair, it's not like all is bad. I think the fact that we have these benchmarks like ImageNet, that as I mentioned, support progress in a measurable way for a decade is really a success. The graph could have looked quite differently, but the fact that it's such a nice line is, I think, really good evidence that yes, there's progress, and these benchmarks are a good way of measuring that. But on the other hand, our conferences are now getting up to 7,000 papers submitted per year. So we have multiple conferences. So I think there's a real challenge for the field how to distill sort of broad, reliable knowledge from this large set of papers we are publishing. So I think we all agree that what we need to do if we want to have machine learning in these safety critical domains I mentioned earlier, we need to sort of convert machine learning from the way we are maybe doing it right now, is a sometimes speculative area of science, into a field that looks more like a reliable engineering discipline. This is going to involve many facets, both experimental work and theoretical work. As Kevin mentioned, my background is actually on the theoretical side. I did my PhD in theoretical computer science, and I'm really excited about working on both aspects here. But I think one key point that is going to be important is that we need to have experiments to test and build foundational understanding. There's a quote that I like a lot by Henry Margenau. So Henry Margenau was a German-American physicist and philosopher of science. And he said measurement is the contact of reason with nature. So on that note, I'm going to leave you with my favorite ImageNet plot, and I'm happy to take questions.
Thank you, Ludwig. Thanks for a wonderful, wonderful, wonderful talk. So if anyone has any questions, please just type hand in the chat, and I'll be happy to MC. Jamie.
Hey, thanks for a great talk.
Thanks.
So I had a question related to the Kaggle plots you talked about. How many of those competitions were image classification?
Oh, that's a great question. And off the top of my head, I don't know exactly, but not the vast majority. So what you often get in Kaggle is, oops, this is too far now. What you often get in Kaggle is sometimes NLP tasks, or you have time series data and the companies want you to help them predict what a customer is going to do and so on. That's a good question. We should look that up. But I mean, okay, I don't want to say a number now, but I think probably more than half is not images.
Okay, specifically for the cases you looked at, is that the case? Most of the ones you were looking at weren't images?
Yeah, so I'm trying to remember which are these four. So I think out of these four, I would guess maybe even all of them are not images. It's a great question. Yeah, I mean, let me look that up. We're having dinner later today, then I can tell you how many of them are images. But I think it's fair to say that more than half of them are not images.
Great, thanks.
I think it's actually fewer, but I want to be conservative. So I'd say more than half is not images.
Jennifer.
Thanks for the talk. I'm having difficulty understanding part of the, so you redid this ImageNet like test set gathering, and you used mechanical Turkers, and then you had this comment about like the selectivity, and there was like a threshold there. And then you also talked about, you look at human performance. And something I'm a little bit confused about is the people on mechanical Turk are also humans. So yes. Presumably, like kind of two questions. One, presumably there's some sort of like test set accuracy. Like you don't just have to have these 5 people that labeled yes. examples. You could also ask like, how did the mechanical Turkers do? And yes. then also, I guess the fact that, I don't know, that you said like, I mean, it looks like with these selectivity numbers, and I don't remember exactly what selectivity was here, that it looks like in some sense it's hard for the mechanical Turkers to get this right. So I guess I'm also a little bit confused how your accuracy plot showed humans doing so well.
Yes, okay, this is a great question because I think that gets an important distinction here. So important point about when building these data sets like ImageNet. When you build ImageNet, and you never ask a human to classify the same way you ask a network to classify. The only decision that humans make when building a data set is, here's an image of a bow, should we include that, yes or no? Humans make only these binary decisions. Humans never are given a single image and say like, which of the 1,000 ImageNet classes do they belong to? So during dataset construction, you only have humans filter, not classify. So all these selection frequencies here are measures of how do humans react to the images for the filtering task. These are not comparable directly to human performance when you ask humans to classify images. So what we had humans do here for this plot was, here humans actually did this thing. You show them an image, and then which of the 1,000 classes does it belong to? So why are things set up that way? In order to classify ImageNet, you actually need to know a lot about the class hierarchy. So ImageNet, as I mentioned, has 1,000 different classes. 120 of them are dog breeds. We learned a lot about dog breeds as a result of this experiment. And I don't think it's, you can't expect Turk workers to know these 1,000 ImageNet classes. It takes a long time to basically become good at ImageNet. And this is why we will eventually do this also on Mechanical Turk. We are obviously curious how well Mechanical Turk workers do on that. So this is definitely on our to-do list. It's a good question. But I don't expect them necessarily to do well. And I don't think it's going to be that meaningful, given the large ImageNet class hierarchy, to ask untrained humans to do this. So I think, yeah, thanks for pointing this out. I think this is quite helpful that people understand the distinction between selection frequency as a measure of image quality and then human performance on the actual classification task. So I hope I clarified that, but if it's still unclear, please let me know.
Thank you.
Ludwig.
Hey, so I think one of the main takeaways was that models still have like issues with shift of the distributions, right? Like, yeah, distribution shifts. So how does this translate to transfer learning? Because, I mean, as far as I understand transfer learning, the promise is that you trained on a certain data set, like a certain distribution, and then you do the transfer on a different distribution, right? So does this imply that maybe transfer learning shouldn't work as we expected, or?
So that's a great question. So yes, I think there's a whole, you're right, there's a whole variety of different ways you could tackle that question. And I think depending on the overall problem you are looking at, some ways are more appropriate than others. So I think the way I interpret transfer learning at least is, here's some data from the new domain, let's fine tune on the data from the new domain, and then we evaluate on test data from the new domain. What we're doing here is different. The images, the ImageNet models are just trained on ImageNet, and we evaluate them on a new test set, which is very close to the existing ImageNet distribution, but the models have never seen our new test set or training data from our new test set. Obviously, we were also curious, okay, is this easy to fix? We did some experiments along the lines of transfer learning. If, let's say, we have our new CIFAR 10 test set, I just fold some of the images from our new CIFAR 10 test set into the training set, and then I train on the combined training set, but that doesn't help. And we have some more work on that direction now. I'm happy to elaborate that now or later. But it looks like these data sets are harder, not just different. That's one note there. And I think for these test sets, I think in the end, if we want reliable machine learning, the answer can't be every time you see a performance drop, you need to train, right? Because then every time you make an error, you would say, oh, it's not the model's fault, we just didn't train on this thing. At some point, you really need to expect, okay, that for some distribution shifts, the models have high performance on both distributions, because as we've seen, humans can do it. So it's not sort of information theoretically impossible.
Yeah, so I have, I'm wondering about sort of whether old style techniques coming out of like pack learning, so boosting techniques can be used. Do you see any sort of possibility about using them to kind of come up with a variety of distributions in order to improve what's going on? Or
so when you say come up with a variety of distributions, so the way I think about boosting, and if you have a different perspective, please let me know, is as a way to construct classifiers. So we could, for instance, try to build a classifier that does well on the harder examples. If we say that Cipher 10.1 and ImageNet v2 are harder, maybe we can upweigh certain examples in the existing data set in order to do better on the new data set. So boosting like that. And yeah, we have done some preliminary experiments in this direction. So far, the answer is no, but I think it's a very interesting question to explore this more. So what techniques do we have in order to make a model more robust to distribution shift? And there's a lot of stuff out there. I mean, I had this one plot where we took everything that people have proposed in the sense of pre-trained models. There's obviously much more out there, which is not yet a pre-trained model. So I'm very interested in sort of evaluating how well current approaches do on this. So far, it looks like it's a hard problem and current approaches don't help. But yeah, if you have sort of concrete ideas, please do let me know. I would be happy to try that.
Linda.
Yeah, I was excited by your talk because we have a problem that kind of fits into this. I was looking at my students' results today, and we have a data set on melanoma cancer divided into 5 classes, and class 1 is benign. There's nothing wrong, even though there was thought to be enough wrong to do a biopsy. And class 5 is melanoma cancer of the worst kind. And my students are developing sort of new approaches that are not just throw it at the deep learning classifier, but one of the doctors asked us, can't you just try throw it at the deep learning classifier to just separate classes 1 and 5? So the students tried that, and to our surprise, it did not come out 100% classification. What came out was maybe 74%, and it turned out that it was slanted in favor of class 5. And on looking closely, it turned out that there were about twice as many samples of class 5 as class 1, because they had purposely sampled more of the more difficult classes. So we were discussing what we would do next and whether we would try to augment them and whether we would try to use GANs. And then I realized that a few weeks before we all went into shutdown, one of the students had gone over to some office on the Ave and obtained another whole set of samples was given to us. And we have never looked at them yet. And I'm saying it was obtained in an office on the Ave, but they're actually digital, and they were put onto our disks. And there's like another data set, just like what you're looking for.
Yes.
Somebody had blessed us. They had another set of samples collected from the same patients, as I understand it. So now I'm thinking, boy, we better start using these right off. We should not have just put them into deep freeze. So the question is, what is the best thing to do? My first idea instantly was to grab 31 more samples of benign and throw it in and see if we can do better, just because we have a deadline for the report of the grant coming up in a few months, and we'd like to show really good classification. But maybe there's something else we ought to do before we spoil those new samples.
Yeah, no, that's a great question. I think at some level, what I'm saying is we tend to, at least for reasonably large test sets that we've looked at in Kaggle, MNIST, Cipher 10, ImageNet, Squad, it seems hard to actually spoil samples in the sense that we tend to not overfit through test set reuse to the samples. So I wouldn't be that worried about that aspect. I think what you could do, which could be quite informative, is if these new samples come from a different data set generation process, like maybe it's a different hospital or different patients or was collected with a different method or something like that, using both of them as test sets could be quite informative to see how well does your method generalize to data from a different distribution.
Okay, but it's not a different set of patients. It's the same patients, different biopsies of the same patients.
Okay.
And that's why it could be very helpful to us to make additional data, but it's sort of like you tried to make more ImageNet. It's like we suddenly got more samples of the same patients without having to do anything because they gave it to us?
Yeah, I think the first thing I would try is to make sure if they're actually from the same distribution, you should get the same performance. If that happens, then it's a good test that at least sort of you're generalizing across these two data set collection processes.
Okay, we'll try that first, and then I'm going to grab 31 of the benigns.
Yes.
Just to see.
Yeah.
Rajesh.
Yeah, nice talk, Ludwig. This is a question that we've been trying to answer that perhaps you have some insights on. So the problem is, you trained your network on CFAR10, and now I want to generalize it to CFAR100. And the network, at least all I wanted to do is at least tell me that it's a novel class, right? And I think at least from the conventional, traditional deep learning point of view, these networks are pretty highly confident, even if I give you, the 11th class from your CFAR10 sort of classes that, hey, it's one of those 10 classes that I've been trained on. So at least the insights that I've heard about in the last maybe a couple of years ago was that you need to truly model the generative process itself, as opposed to training it on a CNN. So any insights on how to tackle the novelty detection problem when you go from CFAR10 to CFAR100?
That's a great question. It's not something I've worked on myself. I know that people have studied this and have come up with decent baseline methods and sort of compared across different methods. So off the top of my head, I would look at one or two of the papers Dan Hendricks has written on this, sort of this out of distribution detection problem, and go from there. Yeah, I can send you a link to that later. I don't remember the titles off the top of my head, but it's definitely something people have looked at intensively.
All right, great. So I guess the idea is not necessarily that you have to model the whole generative process.
No, I don't think that's what they're doing there. I think they're basically using confidence plus some modifications at the top.
Okay, that's interesting. Yeah, thanks. I'll look it up. Great.
Okay, well, we're over time, and thank you let's thank Ludwig again, and send him off. Thank you.
Thanks.
Thank you.